Swayam Prabha, Digital India, Educated India.
Today is the first day, and therefore I'm just waiting a little bit for everybody to join. I'll just tell you how we will try to make this class as interesting as possible in this online platform. I request all of you to sit with a pen and a notebook. I do not want you to just listen to me with folded arms like this, relaxing in your chair. Then you will miss the basic flavor of the class. So it's a very conventional class. I do not have any PPT to show, no videos, nothing, right? So continuously these notifications come, it becomes difficult to read the chats, right? So better you sit with a pen and paper or a notebook and a pen. The best mode to get the maximum flavor of my class is to treat the screen as the board, and exactly what you do in your classroom as the teacher writes on the board, you copy it. So that's going to be the best option. This PPT slide which I am using for teaching, that's the advantage of technology, that also I will save, and it will not show up in your Microsoft team, but through ERP or some common mail, I will also send that, maybe in a modular fashion. So once I finish a module, I will send it. So again, a formal welcome to process calculation, my part, that is essentially the energy balance. I'm sure Arnav has given an overview of what he is going to teach. He's going to teach about mass balance. So essentially the two vertical splits that we have between the two professors is primarily based on what type of conservation you are looking at. So essentially whatever Professor Otto is going to teach primarily relies on the basic concept of conservation of mass, and I look into the energetic aspects. So there are several processes where energy, conversion of energy from one form to the other, or transfer of heat, all these things are sort of relevant. So let me also tell you that so you also have to give me some time initially, because what I teach initially may look like very boring to most of you. Also, I forgot to share my screen, so let me do that. So these are the contents of my part, what I'm going to teach. So energy, the basic thermodynamic terminology and concepts. Let me tell you, it's nothing but, at least first couple of lectures is going to be likely to be very boring. We will try to make as interesting as possible, because you know it all. It's the basic thermodynamics. But maybe today itself you will start realizing that we will visualize the stuff you have studied maybe in your 12th standard for your JEE preparation, and also for your first year chemistry thermodynamics. We will be talking in a slightly different manner. How it is different? Because we will try to do two things. One is, of course, this is a level 1 engineering subject. So there are certain differences in approach between of an engineer and a scientist. All of you essentially are have so far studied science. You did very well in JEE because of your excellent knowledge in science, and that gave you admission in an engineering program. So that's the real twist of fate. Reality is there is a difference in approach, so that I will clarify. I mean, maybe in science, whether the value of G, I'll pick up an example straight away, whether the value of G is 9.81 at mean sea level, and if you go up to, let's say, 10,000 feet, whether it changes to 9.805, this matters a lot, right? But even when you were writing your JEE exam, what was the value of G you assumed? You assumed it to be 10. So that is what is called the so-called engineering approximation. So an engineering approximation essentially, am I still audible? Yeah. So engineering approximation, or the genesis of this approach, is that we always trust in something is better than nothing, right? So estimation is a major thing in any type of engineering problem. So whatever is written here, introduction to energy balance without chemical reaction, estimation of physical parameters. So let me give an example of energy balance without chemical reaction. All of you can do it with your eyes closed. Let's say 100 milliliter of water, you are heating from 30 centigrade to 70 degrees centigrade. What is the energy requirement? This can be a problem, right? In fact, when you use a geyser in your bathroom and when you design that, this is exactly the calculation you do. So you say, what is there to know? I mean, we know everything. What do we know? We know essentially, we know the mass, we know the Cp, and we know the delta T. So therefore, Q is equal to mCp delta T, right? All of you will do that, and you will get the numbers. But there, while you do this, right, you have taken something for granted. What is that something for granted? Can you reply? So mCp delta T, everybody understands, right? And then you can calculate. So my problem statement is 100 grams of water or 100 ml of water I would like to heat from 30 degrees centigrade to 70 degrees centigrade. What is the heat requirement? You can all calculate that. I'm assuming that you can all calculate that, of course. But when I say that you can calculate that, you are taking something for granted. What is that? Cp remains constant with temperature. Cp remains constant with temperature. Cp assumed to be constant. Constant value of Cp, very good. But even more than that, you know the value of Cp, right? You know the value of Cp. Those of you who have said it's perfect, Cp is constant. But then again, when you say that you are worried about whether Cp remain constant or Cp, no, heat loss is not the correct answer. Whether Cp remains constant or Cp is a function of temperature, you are actually very critical. Whether Cp is same at 30 degrees centigrade or 50 degrees centigrade or 70 degrees centigrade. Of course, we will solve some problems where you have Cp given in the form A plus Bt plus Ct square, and then you know that you do not do mCp delta T, but you essentially do a mCp integral delta T from T1 to T2, and then you need to bother whether your temperature is in centigrade or in Kelvin, whether the expression that is given is in Kelvin or centigrade and all that stuff. But what is more important is, this is where you are still kids and you are still science-minded kids, is that you are assuming that at least the value of Cp is given. So it's like still a question paper, the value of Cp is given and you just do the calculation. In real life, unfortunately, you come across a liquid, you go to a lab, some liquid is there, and you may know the chemical composition, and you don't know the Cp value, but you still need to, as an engineer, you still need to come up with some number. How do you do that? So that is exactly what I'm going to teach you when I talk about this part, right? Estimation of physical parameters. It's not only Cp, but, sorry, just give me a minute to adjust my slope. Yeah. So this we will see what exactly, how we can get a first level approximation of these physical parameters. Then we will look into calculation of change in enthalpy type of situation. Then after some time, we will look into energy balance with chemical reaction. Don't forget that 2/3 of the class is chemical engineer, so we have to deal with chemical reactions. That's where we will start differing from mechanical engineers and electrical engineers, for example. And 1/3 is biotechnologist, and you also have a lot of biochemical reaction. So we all know that chemical reactions are associated with thermal effects. In fact, all of you know this endothermic and what is that? I'm forgetting the term somehow. Yeah, so these type of reactions, right? So we need to look into the thermal effect of chemical reactions, and then we look into. So this is looking very small, but it will take a while before we reach this level. And then we look into something like heat of solution, heat of mixing type of stuff. And then one important thing I will teach towards the end of the course is the concept of psychometric chart. It's a very engineering stuff, in fact used in the refrigeration and air conditioning industry primarily, and all the humidity calculations. Because you will soon realize that there are many processes which significantly gets altered based on the humidity or the surrounding humidity. And one classic example of that is the process of evaporation, right? So if you leave a glass of water, let's say at 50 degrees centigrade and in a very dry environment, or maybe a drop of water on a surface, the way or how fast it will evaporate it will take certainly longer time if the temperature is low and you have a lot of humidity around. So even if this does not make any sense to you, it's fine. We will slowly get started, and you have to give me a little bit of time, because initial part, as I have told, is going to be complete revision. So I will not waste too much time in that. And also, as I was telling that, of course, we need to talk about engineering approximation, but then myself as a person, I'm more inclined towards science. So though I'm a faculty of chemical engineering, I essentially do physical chemistry and physics type of stuff. So I have a lot of keen interest in so we will try to understand many of these occurrences which are taken for granted in our surrounding or in nature. What is the physical genesis of that, right? So we will see how it happens. In fact, with whatever knowledge you have so far, many stuff that happens around us, you can start explaining, right? So we will try to make that connection between what we learn here and what we already know. So many things you will see that you know it, you have somehow studied it, read it. If I ask you, this happens, you will immediately say, yeah, this happens. But you will find slowly that many of these things can be very nicely, my voice is breaking, I'm sorry, I just can't do anything. It's a network connectivity. I do hope that the voice, and is this voice breaking problem common to everyone? Or it's only to Arjav? Okay, so Arjav, it's network at your side. I'm sorry about it. That's why we are recording the video. Try to follow as much as you can. All right, thank you. Try to follow as much as you can. And then if because of, yeah, Arjav, I took note of your fact that, took note of your concern that you said that my voice is breaking, but your other friends are telling it's not breaking. So what can I do? I can't do anything about it. So please check the network connectivity at your side. So let's stop this discussion. So many things that we have taken for granted, or we know the definition, you will find that we can sort of explain it very nicely with some of the basic concepts which are related to all this energy balance and stuff like that. I can come up with a couple of examples right now, or maybe let the class unfold a little bit and then I will talk. So the textbook that I will follow is primarily the second one, the basic principles of calculation of whatever is the name in chemical engineering. It's called the Himmelblau's book. And those of you, I request all of you, if you are still not there in WhatsApp, kindly join the WhatsApp group, because I have already forwarded, assuming that some of you might not be having the book, I have already forwarded the soft copy of the book here. So the tutorial problems I will take up from here, or I will send you tutorial sheets or whatever. There is another book, this Chemical Process Calculation by Haugen, Watson and Ragutz. It's a very orthodox classical book. Some concepts I may teach from there, but this book has a problem because its older editions all come in, all the calculations are shown in FPS system. So it's not a great thing to do. The numericals will be very difficult to handle with cubic feet and all this stuff. So primarily we will be following Himmelblau's book. And for my class, if you follow my lecture notes, that's going to be more than enough. It's going to be very simple, and let's also hope that it turns out to be enjoyable for all of us. So we need to look into, first let us get started with the discussion. So what are the primary conservation equations we know? So we know conservation of mass, and then which in the language, the pedagogy, people write as mass conservation. Then Professor Otto will slowly teach you what is material balance, what is like component balance, etc., etc. Charge is not very important for us. And of course, we also know about the energy balance. And what is the energy conservation equation? It says that energy cannot be created or destroyed, but it can transform from one form of energy to another form of energy. Straight away to the point, what type of system cannot be covered using this energy balance equation? There's only one type of system which cannot be covered. You cannot write this equation. No. Nuclear system is the correct answer, Aditya. Thank you. Very good. Because of the nuclear systems. Because of the famous equation which got the fascination of many of you into science even as a child, because of this particular equation. Next question. What is M? E equal to mc squared I have written, do not repeat it. What is M? What exactly is rest mass? This is a terminology I do not know. I use another scientific terminology. 4 of your friends, very good. In chemistry, they call it mass defect. Good. Those of you who have written it, it's fine. Loss in mass or mass defect. Yes, Samira, hi. Some people, some 10 or 12 guys responded. I assume that all of you know it. You should know it, because also I must tell you that when I'm teaching to the chemical engineering students who are now in second year, I have a special connection with you, because I was responsible for all of your admission into this IIT, if you may recall, as the JE chairman. Yeah, but there are people, there are friends whom you ask what is M, they will say mass. Be very careful. It's not mass, it's the mass defect, or if rest mass is a terminology that is being used in schools or whatever, it's perfectly fine. But in chemistry literature, at least, mass defect is the more valid terminology. So essentially, it's the change in the atomic weight in the nucleus because of the chemical reaction, because of the nuclear reaction that takes place. So we need to get started from a very elementary level, and that is we need to talk about some basic thermodynamic pedagogy. So I will just check. Those of you who said energy balance equation is not valid for an open system, kindly get your concepts cleared. This is a grossly wrong statement. Okay, so the whole class, I guess, knows about these 3 terminologies. So this is my system, right? This is the surrounding, and this is sorry, not this. And this is the boundary. Right, let's draw it again. So we also know about, I'm not even teaching all this, though these are all in your syllabus. So we also know about open system, closed system, and isolated system. So let us say everybody starts discussion with open system. We start our discussion with an isolated system. What are the properties of the boundary that are required? So we all know there is no exchange of mass or energy. We all know that. So my question is, what should be the mandatory properties of the boundary for an isolated system? As I told, we will look into something very simple, but from a slightly different perspective. These longish pauses are because of connectivity issues, because I'm not getting any replies, and then suddenly they will come in bulk and I will miss half of them. Well, first thing is, when those of you write adiabatic boundary, I'm not very impressed with that. Rigid, perfect. Non-permeable, adiabatic boundary. I'll use a better simple word. Yes, Aditya Agarwal. Insulated. I will prefer the terminology insulated, and of course the necessary condition is so rigid. Of course, adiabatic is a perfectly valid word, but I will prefer, again, we will remain very simple. Let me clear that. I do not like pedagogy at all. We should talk science in the level that a 7th or 8th standard student understands. There is no, please do not try to anytime give me an answer which is veiled behind nice words, nice scientific terminologies. I don't like it. Huh? So we all understand. It's insulated and rigid. Perfect. Can the same figure be used for an open system? I have slightly different way of looking at things. Not open system, I'm sorry. Can the same figure, in fact, it can be used also, closed system? How? Of course you understand. So that you just take off the insulation, right? You just take off the insulation, it still remains rigid, and it becomes a closed system. If a closed system is insulated, perfect. Then what change must be there to the figure? I'm talking about a closed system that is insulated. What change must be there in order to ensure that the system is a closed system? Be precise, Rahul Goldar. Volume doesn't make any sense. I am talking about the system geometry and boundary. Be precise. It's also very important, particularly in our online mode, that you give the precise and correct answer. So rigid boundaries, again, not the, okay. So rigid boundaries, mass cannot be exchanged, no. External insulated boundary, Bapre. I'm saying that boundary is insulated. My question is very clear. Can a closed system have insulated boundaries? Anyone else? Very good, Abhishek Kumar. Of course, it can have insulated boundaries, but then it must have some movable or flexible part. Absolutely. You can say non-rigid, or you can have a movable part or a flexible part or whatever. Shivoy Dikshit, get your concept corrected. It does not become an isolated system straight away if you have a flexible part or a movable part. Suppose you have a balloon. Right? I do two things. First, I fill it up. Then I after closing. What will happen? What type of system is it? What type of system is it? Okay, all of you, starting from Samira. Samira was the first one to give an answer. Don't fall into the trap that I lay at times. I'm a teacher, but a teaser also. Look at the system, look at the description carefully. First I said I fill it up. When I'm fill it, so now I'm not happy with closed, so somebody starts writing open. Relax, relax. These are real fun to have in the class, in a classroom. Well, you know what happens when somebody gives such an answer? So essentially this type of a question, yeah, now the correct answer is emerging out. If I give this type of a question, somebody will say something, and then people will try to track my face. If my face is becoming smiling, then everybody says, yeah, this guy is liking it. Then everybody will say that. If I say something like this, then immediately the section or the choice changes to the other one. So many of you fell into the trap actually. This particular system, initially when you are filling it up, it's an open system because you are adding mass, right, in the form of air that you are pushing. Then once you tie it, it actually becomes a closed system. It's not an isolated system. Why? Because as you heat it up, let's say from 25 degree to 30 degree, its volume will expand, right? And therefore boundaries will expand. So what precise component, I'm supposed to teach it, but let me ask it. What precise thing does not make it, or what exactly is the mechanism of energy transfer that makes this balloon a closed system in its second part? How is the energy transfer happening? Anyone having any problem in following me, raise your hand or just tell me. Aditya Chawla, your answer is wrong. That does not make it, that is part of it, but not fully. That is not the reason. What is the definition? No, conduction is not the right answer. No, not at all the right answer. What is a closed system? Closed system is, see, such a easy concept, but certain conceptual things needs to be clarified. Expansion work, very good. As the system expands, it's actually doing some work on the surrounding. Yes, absolutely. Now you are talking sense. And what Aditya Chawla and others started to tell is why the expansion takes place. So you must be very precise with your answer, with your understanding. Of course, as you heat up, the kinetic energy of the molecules increase, right? And what increases? As the kinetic energy of the molecule increases, what increases? Some property of the system. Yeah, see, don't repeat things. That is one thing I do not like. Once some people have told, I have told, then do not repeat it. Yeah, volume increases. What other than volume, energetically, what increases? As you heat up the system, right? No, volume is not an energy related parameter. Something else increases. Temperature, of course, increases. What else? What else? Which term related to energy increases? Random energy of gases, kinetic energy, motion of particles. Carry on. Internal energy. Very good, Gaurav Jha. Very close. I'm not fully happy. Not entropy. Not entropy. Entropy we are not talking about. Enthalpy increases. Enthalpy increases. Yes, randomness is associated with entropy, but that's not what we are looking at. Enthalpy increases. That's a very important term for us. Right? We will understand. In fact, that's a very critical understanding we need to have. What is the difference between internal energy and enthalpy? We will talk about it when time comes. So my next question is, so everybody is clear with this very stupid and simple, not stupid, but very simple discussion? Everybody is clear? We know it all. I take advantage of this picture I drew, and ask again a simple question. Can this figure be a representation of an open system. My last discussion, acha, yes, how? Sneha Bandhu, how? Very good. Permeable boundary, don't have to say membrane, porous, permeable, whatever. So very important to note is this is not the only example of an open system, right? In fact, the chemical engineering students have already started to do a course on fluid flow. So this is a pipe through which liquid is flowing, and if you look at section of the pipe, this is also an open system. So open systems can also have boundaries, or there can be no boundaries at all. One side can be open, two sides can be open, or whatever. So I guess all of you understand, I mean, everybody knew this. All of you understand and fully that in thermodynamics, we have studied it from a thermodynamic standpoint, whether mass and energy can be exchanged, only energy can be exchanged, and nothing can be exchanged. But it is more important to now realize it's actually the material of construction of the boundary, the sort of, and the rigidity of the boundary that actually defines the property of the system. Is it clear to all? So essentially, two properties matter. One is permeability, and the other property is sort of whether it is insulated or not. Is it clear? So I'm sorry, I think I should also add rigidity. Whether the boundaries are completely rigid, whether they are permeable, and they are insulated. So it sort of, I guess it sort of throws a new light in appreciating an isolated system, that an isolated system must have rigid boundaries and which are insulated as well. Is it clear to all now? I guess it's clear to all. Now, to summarize, or not even summarize, to sort of finish this, we would like to pick up an example of each one. Open system, right from glass of water to some air in a room, right? Everything is an open system. When your air conditioner is blowing in your room, it's actually your room is an open system, right? Closed system, example of closed system. Meteorite and all that are exceptional cases. You do not have a meteorite hitting every day. So when we are talking about something, so that's exactly the correct answer. I said Earth is actually a closed system under certain approximations depending on where we set the boundary. Where we set the boundary, certainly not on Earth's surface. We set the boundary around our atmosphere, right? So gases escape and all that is sort of debatable question. Not exactly debatable, they do not happen. You know the atmosphere is, well, I will stop this space mission business. Space mission is not a natural phenomenon, right? So kindly stop that. When you send a spacecraft, when a meteorite crashes, when a spacecraft crashes or something like that, these are, none of them are sort of occurring every day. Those are exceptions, right? And space, when a rocket comes back, in fact, rocket was initially built in the Earth. So its mass was part of the total mass of Earth. So when it goes and comes back, if it ever comes back, right, then again, its sort of mass is balanced out. Now, don't say that conservation of mass is not valid because from time to time, all the space agencies send rockets to the universe. Don't say this. So if you don't say that to contradict conservation of mass, right, then please do not bring up these examples to contradict what I'm trying to explain. And I will carry the whole class with me. I will convince you why I talk about it. On the whole, along with its atmosphere, because of gravity, sort of everything is sort of stuck around the Earth, right? Even if you consider satellites, this, that, they are all rotating. Beyond that, we all know Earth receives energy from the sun, right? So therefore, since energy is coming from the sun, it sort of falls into or satisfies our condition of a closed system, that there is exchange of energy, but there is no obvious exchange of mass, right? Earth is not sending couriered mass, sun is not sending couriered mass every month to Earth. So mass of the Earth as a planet, as a system, along with its atmosphere, without the satellites, without the meteoroids, is constant, right? Therefore, mass is constant. However, on an every minute basis, there is exchange of energy. So what type of system is that? Sneha Bandhu Singh, would you write a mass conservation equation, or you will always write the total mass and energy combined is constant? Sun sends regular energy, so there is no contradiction. Open like helium gases escape. So there is a. So I'm not talking about the sun. Sun, of course, it comes, but that helium does not necessarily come to Earth only. So I said it's a closed system. It's a good example. That's why I picked it up under certain approximation. Please also understand that we are not learning earth science here. So therefore, there is no point in, and there is absolutely no fun in contradicting me with all these nitty-gritty, super nitty-gritty details to prove that I am wrong. What example I have given is 99%, all of you are convinced. You are just now try on a fault finding mission like the space mission somebody is mentioned. That does not help. Change this attitude. It really doesn't work. On the whole, most of you agree, I'm sure by now most of you agree that Earth is a reasonably good example of a closed system, right? No, there is nothing to be sorry. Absolutely nothing to be sorry. This is all in the true spirit of science. But we sometimes get carried away because of our intelligence. All of us are, except me, all of you are extremely intelligent people to find out the minutest details, right? So that really should not be the approach. Approach is something that is generic, and generically, yeah, all this you are writing, no, interconservation of mass and energy. Yeah, why do you talk about it? Because you cannot capture a nuclear reaction based on the energy balance. So therefore, you have to talk about mass and energy together. But that's quantum mechanics, right? That's relativity. Are you going to talk straight away about relativity in your second year? Do you know that? Are you competent to solve problems? No, the answer is no, you don't know that. All you know is very classical physics so far. Okay, see, it's 50 minutes gone. We have not started talking of anything substantial, but doesn't matter really, as long as you are enjoying. Now the most exotic one, example. Example of an isolated system. Hot water in a thermally insulated flask. Why hot water? Why not water in a thermally insulated flask? Universe. Anything else you can think of? Yes, universe is a closed isolated system, of course. See, but then again, what is the boundary of the universe? Isolated system must come with a rigid boundary. Are you sure universe has a rigid boundary? So in exactly your spirit, I have not yet lost the spirit of contradicting, right? So that's it. Let us all be good friends and enjoy what we are doing rather than mugging stuff. I don't care whether we talk about just one slide and some stupid examples in a class, as long as we enjoy. So all of you have read somewhere. This is exactly what I tell. All of you have read some examples of a closed system to be universe, or sorry, an isolated system to be universe. And then 15 minutes back when we were arguing that the nature of the boundary determines whether a system is isolated or closed, and the necessary condition, calorimeter, no, certainly not. It's just sort of a artificial system, not a great example. Thermoflask is a slightly better example, because you have to heat up a calorimeter. So when I was telling that the necessary condition for having an isolated system is like to have a rigid boundary and which is insulated, about universe, you don't know either. So we of course take universe as one of the classic examples of an isolated system, and in the same spirit, we actually take the example of Earth as a closed system. Well, there is something that happens in our nuclear plants. I don't know exactly how it happens, but all the nuclear waste that is disposed, they are typically closed systems. They are typically isolated systems because you do not want any nuclear waste to diffuse out and mix with the surrounding, right? So that's an example. You can just go to the Wikipedia. By the way, whatever textbook I have suggested, apart from that, Wiki is a great place to learn. So for all my scientific doubts, my first contact point is Wikipedia, right? Perfectly black body, yes, to some extent, of course. But not fully. I think if I get a chance to teach you heat transfer, I will show that. Okay, so I think this part is now clear. Closed system, open system, isolated system. Okay then, so with that I will stop. Thank you very much for joining.